All right, well, I will leave these and get started then, I guess. All right, so I think I want to finish up what I'll call basic NMR spectroscopy today. In other words, things that all sort of fall at the level of basic interpretation of structures, and in turn things that we'll get on the midterm. I think probably where I'll pick up next time is going to be introducing 2D NMR, and then our next homework set, not Mondays, but the one after that, we'll start using 2D NMR spectroscopy. So what I wanted to do today was to talk more about carbon-13 chemical shifts. And I gave you, when we talked last time, I gave you this sort of general information that just like proton NMR, carbon NMR, aliphatics tend to be upfield, aromatics tend to be downfield. Things that are next to electron withdrawing groups, particularly oxygen, tend to be we'll call it midfield, sort of in that 50 to 70 range. I also indicate, and we said that the range is a lot bigger. It's about 20 times bigger in ppm for C13 NMR. In other words, an aldehyde CH is at roughly 10 ppm, whereas in carbon NMR, an aldehyde carbonyl is at roughly 200 ppm. So it's sort of like 20 times bigger range. Now, C13 shifts have a bigger range, and there's also more richness. In other words, when we talked about proton NMR, it was pretty easy, and we were able to come up with some really simple, back-of-the-envelope calculations where you could typically peg the chemical shift to within, a few tenths of a ppm. We talked about if you're next to an ester, or if you're next to an oxygen, figure you're going to be about 2 ppm downfield of where you'd normally be. If you're next to a benzene ring or a double bond or a carbonyl, figure you're about 1 ppm further downfield. And I gave you several ways of thinking about this, and you should all be able to pretty much estimate things. We talked about the effects of alpha substituents and said that alpha substituents have a really big effect. Being next to a CH, next to a halogen, next to a nitrogen, next to an oxygen, shifts you down a couple of ppm. We talked about beta effects, and we said that they're smaller. Beta effects in proton NMR shift you down by like 0.2 to 0.5 ppm. C13 NMR is a little bit more subtle and a little bit, I won't say less predictable, because we're going to see it's actually quite predictable. But there are more factors. For example, gamma effects as well as beta effects tend to be big, and there are some really interesting steric effects. Now, along with this richness comes tremendous power, because this means that carbon NMR also can give you tons of rich information about structure and can be really useful for figuring out structures, confirming structures, disproving structures, and at the end I'll show you a beautiful example of some fraudulent work that was disproven by Professor Rachnovsky's laboratory, and also going ahead and basically having a tool that can get you a lot more information than meets the eye. So I want to show you some of the factors that contribute to these sorts of general ranges, and particularly now perturb them. And let's start with something pretty simple: inductive effects and resonance effects. And electron density, of course, plays a huge role in chemical shift because electrons contribute to the shielding or deshielding, if they're absent, of various nuclei. So if you have substituents that increase or decrease the electron density in a carbon, you're going to shift that carbon upfield or downfield. Let me show you what I mean. We'll start with a simple benzene example. Now, the easiest way to, in your mind, think about chemical shifts is to start with a base value and then perturb it. So a great way to think about benzene is the normal position for benzene is 128.5 ppm. And then if you put substituents on it, you perturb things in a rational way. So let me show you what I mean. If we put a methoxy on the benzene, the oxygen is electron withdrawing through the sigma bond. And so the carbon attached to the oxygen shifts substantially downfield. So you go to 160 ppm. In other words, you shift downfield by 30 ppm, more than 30 ppm by putting that oxygen there. Now, what's interesting then is the orthocarbons end up having, by resonance, extra electron density at them. In other words, the two orthocarbons, you can push your arrows, and you see they're electron rich. It's the same reason why electrophilic aromatic substitution occurs ortho and para when you have a methoxy group on there. So the orthocarbons appear at 114 ppm in methoxy benzene. You don't get a big effect at the metacarbons, which makes sense because you have inductive effects that are now quite removed, so it's very small, and resonance doesn't pump up the electron density at the metacarbon. You go to the paracarbon, and now you also see an upfield shifting, albeit a smaller upfield shifting of 121 ppm. Now, I'll come in a moment to empirical additivity relationships, but one way to think about this is to think about it if you have a methoxy group or an alkoxy group on a benzene, that it shifts the orthoprotons upfield by about 14 or 14.5 ppm. And if you have a methoxy group, it shifts the paraprotons upfield by about 7.5 ppm. And if you have a methoxy group or an alkoxy group, it shifts the metaprotons downfield by just a fraction of a ppm. And what we'll see in a moment is that you can add up all these effects and then calculate for different aromatics the effects of different substituents. All right, let's take a look at some other examples of inductive and resonance effects. So let's take an alkene, and I'll give you cyclohexene as a base value. In cyclohexene, your alkene is at 127.4 ppm. Let's compare that to cyclohexanone. And in cyclohexanone, we see a very big effect at the beta position and just a little effect, just a little inductive effect at the alpha position. The beta position is 151 ppm, and the alpha position is just shifted downfield by a hair. And that makes sense because you look at this and you say, okay, now you can think of a resonance structure in which you're electron deficient, right? We all know that enones are Michael acceptors, that nucleophiles like to attack at the beta position. Are you doing this with orbitals in Van Vranken's class now? Yeah, so you know about frontier orbitals and electron density. And so you see the effect is actually very substantial, right? Both of these carbons, they're symmetrical. They're at 127. You go more than 20 ppm downfield by decreasing the electron density. These effects can be absolutely humongous. And one of the things that I've tried to emphasize when I've talked about these ranges here these are general ranges. These are not carved in stone. And so you already see, for example, that this one inductive oxygen here brings us even outside of this very generic range here. Let me show you just how huge the effects can be. So ketene acetal is a good example, right? Alkenes are normally like 110 to 150 ppm, but if you hugely perturb the electron density, you can have huge effects. So it probably doesn't surprise you too much if I tell you that you now, by having two methoxys on an alkene, can shift it downfield to 169.7. But what's really huge is you look at the position here, the beta position on the alkene, and now we're so electron rich. This thing is so nucleophilic at this position. There's so much electron density at that position that we're at 45.5 ppm. You look at a spectrum of that, you wouldn't even know it's an alkene, because you'd say, oh, that's got to be aliphatic. That's got to be somewhere over here. And we've just pumped up the electron density hugely. The most radical example I know off the top of my head is this sort of push me, pull you system here, where you have two electron donating groups and then two electron withdrawing groups, two cyano groups. And so this alkene, you go to 39.1 ppm. And then this carbon here is at 171. And 171, you'd say, all right, well, that's really downfield, but you'd say it makes sense. You've got these beta electron withdrawing groups. But you look, 39.1, who would have thunk that that is an alkene? Yeah.
What is that letter next? CW or CN?
CN. Two, okay. So these are two nitrile groups. These are two cyano groups, CN groups.
Okay.
All right. So substituents have substantial effects, whether they're alpha, whether they're beta, whether they're gamma. And you can really see this. I'll give you, we're going to walk through this, and I'll give you some examples. So first, let's talk about alpha-alkyl substitution. And if I want to give you a general principle, in general, alpha-alkyl substitution leads to more downfield shifting. So if we, again, take our benzene example, and remember we said that benzene was at 128.5. If we put a methyl group on it and make it into toluene, now we go to 137. Point is, we shift downfield by about 9 ppm by putting on a methyl group onto benzene. Let's take a look at alkyl systems. So we'll look at propane. And we'll look at the central methylene of the central carbon of propane. You put on an alkyl group onto propane, and you get isobutane. And now you're down at 25 ppm. And so you notice it's kind of about the same. Here we move down by about 8 or 9 ppm. And here we again move down by about 9 ppm. So in other words, we're talking on the order of 10 ppm or thereabouts. All right, you put on another alkyl substituent, and the effect isn't as dramatic. But again, you move further downfield. Now we're at 28 ppm. Now, what's nice about this is these ideas are generalizable. There is really science here to it. And this is the point, that you can take little bits of knowledge and generalize and build up in your mind what's going on. So let me compare us, say, to ethanol. If we start at 58 for ethanol, and now we envision going to isopropanol, what would you predict your carbon to be at here? 67 would be a very good prediction, because we say, OK, we take 16, we add 9, we get to 25. You add 9, you get to 67. And that's a very good guess. 64 is the answer. All right, now imagine we go further and we go to tert-butanol. Now what do you think for tert-butanol? 66?
I don't think it's going to change.
You don't think it's going to change? Okay. Other guesses on this, estimates? 67. All right, and the answer is 69. No, you're doing good. You don't have to peg it to the nearest ppm. Oh, okay, the Price is Right approach. The chemical shift is right. Do you think we have a show here? Maybe really late night TV? Ooh. Maybe we can do a webcast of this. Try it out in a test market. All right. So in the case of proton NMR, we also saw that adding a alkyl group shifts you downfield, right? We said a methyl group is typically at about 0.9 parts per million. A methylene group, we said 1.3 to 1.5. So in other words, you're shifting down 1.2 to 1.4, I think I said. So in other words, we're shifting downfield, to about 0.5 ppm. A methine is down at like 1.5 or 2 ppm. These are the baseline values. So in other words, we go a few tenths of a ppm more. And so it kind of makes sense if you get half a ppm for adding one alkyl group and another couple of tenths of a ppm for adding another alkyl group. Kind of makes sense here with a scale 20 times bigger that we get about 9 ppm or 10 ppm for adding one alkyl group and about 5 ppm for adding another alkyl group. With the case of proton NMR, beta alkyl groups don't make a huge effect in chemical shift. In the case of C13 alkyl groups, though, they do. Beta substitution ends up also leading down to further downfield shifting. Not quite as dramatic. But let's take an example. And what I'll do is I'll take butane as an example, and we'll look at this carbon here. And then we're going to put substituents over here. So there'll be beta to it. In other words, instead of directly on it, there'll be one over. So if we add one methyl group here, so I'll go from butane to methylbutane. Now, this carbon goes 7 ppm more downfield. We go to 32 ppm. And then if I add another one, we go another 5 ppm more downfield. We go to 37. Not as big, but still pretty darn big. OK, so that's beta substitution. Let's look at gamma substitution. Now, gamma substitution is interesting because gamma substitution leads to upfield shifting, and it's really a steric effect. So with gamma substitution, what basically you're doing is now getting interactions that are, by having steric repulsion, pushing more electron density onto the carbon and shifting you upfield. So let me show you what I mean. So we'll still keep to this same type of general structure, but now we'll consider this carbon here. And so if you look at the carbon here, and you have hydrogens banging into it, you basically will have hydrogens banging together. This is going to lead to more electron density on the carbon. In other words, electrons of the CH bond repelling electrons push electron density into the carbon. And since you don't want to have steric repulsion, this occurs most pronouncedly when the molecule cannot avoid steric repulsion. Let me show you what I mean. In other words, if we start with butane, and we start over here, the methyl group of butane is 13 ppm. If I add one methyl substituent, gamma, so right, in other words, if I attached it directly to this carbon, we'd be alpha. If I attach the methyl substituent here, we'd be beta. If I attach the methyl substituent here, we'd be gamma. If I add one methyl substituent, that carbon shifts from 13 to 12. And you'd say, that's not a big deal. That's not a huge effect. And part of it is this methyl group can adopt a rotational isomer, rotamer, where it keeps out of the way. But if I add one more methyl group, then no matter what, we're going to be staring that other methyl into the face. So if I go like that and go to 2,2-dimethylbutane, now there's no way to avoid that steric repulsion, and we shift over to 9. So now we've shifted upfield by about 4 ppm relative to our initial compound. So even this very remote substituent can make a big difference. You can really see this in conformationally constrained systems like cyclohexane. So if I take cyclohexane and I consider the carbons, all the carbons, of course, in cyclohexane are the same, and they're all at 27 parts per million. If I now add a methyl group, gamma, to this particular carbon, so remember, if I attached it here, it would be alpha. If I attach it here, it would be beta. If I attach it here, we're gamma. If I add one methyl group, that methyl group keeps out of the way because it keeps equatorial, and so we don't see any change. But if I add a second methyl group, gamma, then one methyl group has to be axial. And there's no way to avoid 1,3 diaxial interactions. And so now that carbon shifts up to 21 ppm. And that's a pronounced effect. And I'll show you the implications of that in just a moment. All right. So these are all of the sorts of biggie effects in C13 NMR. And now I'll show you the last biggie effect, and that's heavy atom effects. All right, so let's take a look at what happens when you make various halomethanes. So again, it's very helpful to have a baseline value. Methane occurs at negative 2.3 parts per million. So we're going to compare the halomethanes to methane itself. And so we'll look at monohalomethane, CH3X, dihalomethane, CH2X2, trihalomethane, CHX3, and tetrahalomethanes, CX4. And we'll start with X being chlorine. And so no great surprises here. You put a chlorine onto methane, you get chloromethane, and you go downfield. It's 25 ppm. You add another chlorine, you go further downfield, it's 54 ppm. Chloroform, where does that show up at? 77. 77 is chloroform. So you go further downfield, you put yet another chlorine on there, and you go further downfield. And so you look and you say, hey, what am I wasting your time for? This doesn't seem like any sort of surprise. Well, if we move down the periodic table, the atoms get bigger, and they start to have d orbitals, and they start to have their orbitals extend outward. And then we see something very surprising. You put on a bromine, and you'd say 10. And you'd say, well, that's not so surprising. Bromine is less electronegative than chlorine. It's going to shift you less further downfield. You add 2 bromines. You go to dibromomethane. And you say 21. When you say, OK, well, that doesn't sound so surprising. We're moving further downfield. 3 gets a little bit weird because we start to move upfield. And by the time we're at 4, we're at -29. And then iodine gets downright funky. So iodine, iodomethane is at -21. Diiodomethane is at -54. Triiodomethane is at -140. And tetraiodomethane is at -292. And what's happening is the orbitals are extending so far out with these heavy atoms as you move down the periodic table that their electron clouds are actually enveloping that carbon and shielding it from the applied magnetic field. And as you can see, in some cases, shielding it very dramatically. Now, the practical implication for this becomes if you go ahead and do a reaction to, say, make an alkyl iodide in synthesis, and you don't go ahead and look upfield, you may miss your carbon and say, oh my God, I can't see my carbon. There's a parameter in the NMR called sweep width that you adjust. That sweep width is the spectral window that you look at. If you have a compound that you expect to be very far downfield or very far upfield, this is true in the proton NMR as well. If you have a compound that you expect to be very far downfield or very far upfield, you can just increase your sweep width, field width, by whatever number of hertz you like. You type in the parameter SW, get a bigger spectral width, and then you can see, for example, your carbon that's attached to iodine. Same thing with protons attached to iodine. I once took a spectrum of HI. I was doing a deprotection reaction in an NMR tube. And the HI, the peak was at -10 ppm in the proton NMR, which was absolutely wild.
Why, like in the bromine one, that at first it puts it more downfield, and then when you get 3 bromines, then all of a sudden now it pushes it back upfield?
I think by what it is, so the question is why are 2 bringing it more downfield? Obviously, you have the inductive effect pulling away. I think by the time you get to 3, you just have that carbon completely surrounded by the electron clouds. So now you just have electron clouds sticking out in all directions. And then 4, it's just all around it. These are in part relativistic effects. When you're doing MO, when you're doing molecular orbital calculations on heavy atoms, you actually need to have special terms taking into account relativistic effects of the orbitals. All right, so one of the take-home messages from this is there are a lot of factors that go into carbon-13 chemical shift. And for this reason, carbon-13 chemical shifts are very rich and very valuable. And being able to predict them can lead you to lots of useful information on structure that can be extracted, that sometimes can give you a problem-solving tool that you might not otherwise have. And so what I'd like to do now is to show you some of these problem-solving tools and their applications. So we'll talk a little bit now about C13 chemical shift prediction. And we're going to talk about 3 different ways of doing this. One is what is called empirical additivity relationships. That's the simplest. The idea there is we're going to go and say, OK, the effect of an ortho substituent is this if it's an oxygen. The effect of a meta substituent is this if it's a chlorine. The effect of an alpha substituent is this. The effect of a beta substituent is this. The effect of a gamma substituent is this. And we're going to add up all of those effects. If you use ChemDraw and you have one of the more advanced versions of it that does chemical shift prediction, that's exactly what it's doing. Those calculations also for all sorts of systems, aliphatic and aromatic systems, are shown in your book, in your structure determination, the orange book that you have for the course, the supplemental book, and you can do it for all sorts of systems. They do it to a limited extent in Silverstein, and I'll show you that just for aromatic systems. Unfortunately, the ChemDoodle program, which tries to do chemical shift prediction, thus far, they're still very much in development, but they've thus far got it wrong. There is also a small CD, Windows only, that goes with with the orange book in the course with the supplemental book that has some limited chemical shift prediction based all on empirical additivity relationship. Another way of doing this is based on databases, where you come up and rather than simply saying, all right, we're going to have alpha effects and beta effects and gamma effects, you have a training set. And then from that training set or that set of reference compounds, you find parameters that fit them, and then you can extrapolate. So you first interpolate to encompass all of the compounds in the set, and then you can extrapolate to encompass other compounds. And so there are generalized databases, and there are also specific ones. So for example, for various stereochemical problems. And the third way of doing this is going to be by electronic structure calculations. And we're not going to do this in the course, but I'll show you an example at the end. Basically, since carbon-13 chemical shifts come from electron density, if you can calculate the molecular orbitals at an appropriate level of theory to figure out how the electrons are distributed in your molecule, then you can figure out the electron density around any carbon, and hence its shielding from the applied magnetic field. All right, let's take a look at these various methods. And I'll start you with a simple page right out of Silverstein. And Pretsch has the orange book, Pretsch, has a similar table. Oh, that doesn't look good. Ah. Helps to plug it in. All right, so this should be on your handout. And as I said, this is just one of the many tables in Pretsch, but a tool is so much more useful when you actually have used it and know how to use your tool. All right, so this is a table of empirical additivity relationships for substituents on a benzene ring. And literally what was done to make this table was, as we said, benzene's 128.5. So somebody took a spectrum of phenol and said the carbon that's directly attached to the OH of phenol is shifted downfield by 26.6 ppm, or 20, what did I say, 26.6 ppm. The carbon that's ortho is shifted upfield by 12.7. The carbon that's meta is shifted downfield by 1.6, and the carbon that's para is shifted downfield by 7.3 ppm. All right, let's take a look at the following compound, and then I'll give you two spectra, and I'll show you how we'll use these. So let us imagine for a moment that we were trying to distinguish the following compound from other isomers. So let us suppose for a moment that we were trying to distinguish, say, this compound, 2,4-dichlorophenol, from this isomer, 3,4-dichlorophenol. That would be a tough one to do based on coupling patterns because in the proton NMR. Because if you look at the proton NMR, you would say we would expect to have one proton that is split by an orthocoupling. So we would expect it to be a doublet, and its J value would be somewhere on the order of about 7 or 8 hertz. We would see another proton. What would you expect this proton here to appear as? As a doublet of doublets with J values of what?
7-ish and what's
Metacoupling?
3?
3. So we'd expect this to be a doublet of doublets with a big J of about 7-ish and a small J of 3. And this one we would expect to be 3 as a doublet. And you would expect this exact same pattern of coupling here. A doublet of doublets with a big J and a small j, a doublet with a big J, and a doublet with a small j. So we wouldn't be able to tell them apart. But let's look at this compound here and use these principles. If we want to calculate the chemical shift for, I'll just do 3 of the carbons here. So if we were to want to calculate the chemical shift here, we would start with the base value of 128.5. And then we would say, OK, we have an orthoalkoxy. And we'd look in our lookup table. And we'd say, or an orthohydroxy. And we'd subtract 12.7. So minus 12.7. Now, we would then look at the effects. Can we see from this angle? Should I move these calculations over? Let me move this over. 128.5 is our base value. Then we have a orthohydroxy, and so we take away 12.7. Now we're going to look at the effects of chlorine for this compound. And so we have 2 metachlorines. So we'll go to our lookup table, and we'll look at the effect of a chlorine. So I'll draw a line here. And so now we have 2 metachlorines. So we have a metachlorine over here. And that's going to have an effect of plus 1.0. And we're going to have, I guess I should make my numbers line up if I'm going to run a tally. And we have another metachlorine, and that effect is plus 1.0. So we tally all of those up, and we predict 117.8. And now I can do, so that's for this carbon here. Now I can do this next carbon. So you help me out with this calculation for this carbon. So what do we use as our base value? 128.5. And then what do we do for the oxygen? So we add, so the oxygen is meta OH. So we add plus 1.6. OK. And then what do we do next? James?
Add
0.2 for?
The metachloro.
For orthochloro. So we do O-chloro is, you said plus 0.2? Plus 0.2. And then somebody else, what do we do last? Subtract 2 for a parachloro. And so we tally all of that up, and we predict 128.3. All right, I'm not going to do any more. We could do it for all 6 of them. But let's flip to the next page in your handout. And I grabbed from the Aldrich Library of Spectra the proton and carbon spectra of the two compounds. And we're just going to look at the carbon spectrum. And the thing that jumped out at me in the carbon spectrum for a difference that was really cool was in the carbon spectrum of the first compound. Remember, the quats are small and the CHs are big due to relaxation, differences in relaxation time and the nuclear Overhauser effect. And what jumped out at me immediately was that here we have two of the CHs close to 130, and one of them, so two basically downfield of 120, and one upfield, so at about 115. And what jumped out at me here was the dramatic difference where here we have one at about 150, about 130, and then two of them at the range between 110 and 120. And of course, we could do this for the quats. There are there are substantial differences as well. You can see here are your quats. So all I did in preparing for today's discussion was I just calculated for the two compounds. And so we did 118.5 and let's see, was that right? 100, wait. Oh, what did I do? I did my, yeah, I don't know how I managed to tally things up wrong here. Wait, 100 and, let's see, 128, 129, 130. 118 point, wait, 118 point, what was it?
No, that would be 119.2. Oh.
Wait.
I'm sorry, that's minus. I'm sorry, I got lost.
Wait a second. Anyone have a calculator?
Right, we were right.
Was it 128.5? Wait, 117.8. Okay. So I get, I don't know what I was writing down here, 117.8 and 128.3. And over here, I think what did I end up doing? 130.7. And then over here, 115.2 and 117.5. And I think here, 131.7. All right, so the point of this is, even though it might be very hard looking at the proton NMR to assign which isomer we have, by looking at the carbon NMR, you can say, oh, wait a second, okay, the first isomer that has the 130.7, 128.3, and 117 matches this spectrum. And we could do this with the quats as well. So this spectrum corresponds to the first isomer. The second isomer that has the 115.7, 117.5, and 131 matches this spectrum. And so imagine for a moment that you're doing an electrophilic aromatic bromination of phenol. You want to determine whether you got the product you expect. You know you have a dichlorophenol. You don't know the regiochemistry. You can very quickly check yourself. And the good news is these types of relationships generally good to, let's say, plus or minus, let's say, 3 to 5 ppm on the average. So the point is that you can, with very little difficulty, tell things apart. All right. There are many, many more sophisticated ways of doing this. As I said, you can do this for aliphatic compounds as well. With aliphatic compounds, you've got to add up alpha effects, beta effects, gamma effects. There's even a little bit of delta and epsilon effects, so you have to look at the whole molecule. There's steric effects. You can do this easily by pencil and paper, but it's even easier to do it with computer software. And as I said, even ChemDraw in the more sophisticated versions incorporates this. There are other empirical additivity relationships that are out there, and but in addition to that, there are databases that have training sets. So for example, this is just one poster I pulled that's a database approach. And what they were looking at was how well their system that was trained on a training set would predict the C13 NMR of Taxol. And in general, their values were good to plus or minus 1 ppm on the average. And so, for example, they were able to distinguish. Here's another one that would be hard to do by NMR. They were able to use their database approach. And here we have 2 tautomers. And so if you synthesize this molecule, you might not know which tautomer you have, whether you have the molecule with the carbonyl or the molecule with the hydroxy. And it's not so easy that you can take an IR spectrum, because by that point you end up with very strong stretches associated with the CN bonds of the pyridine tautomer. And so the IR spectrum is not clearly going to scream carbonyl at you. The C13 NMR, the difference between what you would expect here and what you would expect here for the carbonyl is small enough you can't just look and say, obviously I have the pyridone, or obviously I have the other compound. But in fact, they can go ahead and calculate to within a couple of ppm. So they were able to experimentally measure the value and then say, OK, what's the deviation? And here they're getting an average deviation of about 2 ppm. In other words, some of the shifts will be off by 3 ppm, some of the shifts will be off by 1 ppm, but on the average, they'll be good to within about 2 ppm. All right, so that's an example of a database approach, and in general, their method's good to about 3 ppm. Many times, you encounter specific problems. You are working on a research project that involves a specific class of molecules. For example, the Rachnovsky group here and the Kishi group at Harvard are very interested in 1,3-diols. 1,3-diols are important classes of natural product. They come from biosynthetic pathways that give rise to molecules of many different structures. And the big issue becomes determining stereochemistry. The Rachnovsky group noticed after the fact they were working with 1,3-diol acetonides. And the question was, do they have a syn-diol or an anti-diol, right? So a syn-diol would be a 1,3-diol where the 2 OHs are like so. And an anti-diol would be one in which they are like so. And the beautiful thing is, if you're a clever graduate student or a clever professor and you keep your eyes open and look at your data, you say, hey, we've got a pattern here, and that pattern tells us something, and that pattern means something. And when they went back and looked at all of their C13 NMR spectra of the 1,3-diol acetonides that they had prepared, they saw something very interesting. The methyl groups of the 1,3-diol acetonides, when the diols were syn, appeared split at about into 2 sets of diastereotopic peaks, one peak at about 20 ppm, the other peak at about 30 ppm. And when they had the syn-diol acetonide, both of the methyl groups appeared at about 25 ppm. In other words, you could now take a diol of unknown stereochemistry, make the acetonide, and just by looking at the C13 NMR spectrum, say, oh, that's a syndiol or that's an antidiol. It's hard to do that otherwise. That's extremely valuable. Why does this occur? It's that gamma effect again. When you make the syndiol, you end up with a chair. And in that chair, one of your methyls is axial and one of your methyls is equatorial. And remember, the axial one gets steric compression, so it is shifted upfield. The equatorial one doesn't get that steric compression, so it's shifted downfield. On the other hand, when you make the antidiol acetonide, then you can go ahead and both your methyl groups are sort of in the middle. Neither of them really has, you get a twist conformation. Neither of them has unusual effects, and they end up in the middle. So just by a quick C13 NMR with this bit of knowledge in hand, you can go ahead and assign the stereochemistry. The Kishi group at Harvard has taken this type of approach with their diols, and this is a really, really cool use of synthesis. So they have diols where you have alternating hydroxy and methyl groups. These are compounds that occur in a variety of different natural products. And so they wanted to be able to tell the stereochemistry of these patterns. So they went ahead and they said, all right, we've got lots of natural products with this type of unit where you have a diol, a methyl, an alcohol, a methyl, an alcohol, a methyl. And so what they did was make a training set of all the possible stereoisomers. So they made ones in which they were all syn, in which one is anti, in which two are anti in different positions, and so forth. And they found that there were characteristics that each carbon in their training set, so they used this molecule as the training set, each molecule in the training set had an average chemical shift of a certain position. And so then they took the average value and they said, if you compare it to the average value, you have a fingerprint where certain ones are shifted upfield, certain ones are shifted downfield. And each of the possible stereoisomers has their own pattern. So that means you can then take an unknown compound based on this training set and the database and take an unknown compound and say, the pattern matches this stereochemistry. All right, last example I want to talk about, and this was really cool. So this is all calculating based on known information. We started with the simplest thing. You just took phenol and you said, okay, what's the effect of an orthosubstituent? What's the effect of a metasubstituent? What's the effect of a parasubstituent? Took chlorine, took chlorobenzene, did the same, and then say you could predict another compound. These diols are also examples where you have a training set. But for really funky and unusual compounds that have very unusual rings and strained rings, there may not be a good model out there. And there was a really cool compound that was synthesized, in quote, by a single researcher in San Diego who published this on his own in Angewandte with no co-authors and no university affiliation. His name was James J. LeClair, still is James J. LeClair. And he published this synthesis that looked really cool because the molecule he said he synthesized was this, hexacyclinol, one that Phil Barron, I think, would appreciate as a challenging target. And like a student who maybe didn't quite get an A in Syn 1, his synthesis had some stuff that was funny about it in addition to him being the sole author. There were steps that just didn't seem to make sense. And so the buzz in the community was something wasn't right here. Now, nobody wants to tell their entire lab, hey guys, let's reproduce James J. LeClair's experiments and see if it really works. That's several graduate students and dissertations worth of work. That's not exactly a great job to be doing. So Professor Rychnowski used electronic structure calculations to see how well he could first predict the chemical shifts of a known molecule. So he took a known compound, ellipsoterin, and did these electronic structure calculations and plotted a graph of the actual chemical shifts versus the observed chemical shifts. And as you could see, most of the chemical shifts calculated, the calculated ones and the observed ones matched within a couple of tenths of a ppm. So in other words, here we have a match of plus or minus 2 ppm on the average. All right, so confident of his methodology, he then took the structure of hexacyclinol, and I'll put this in quotes here, as you'll see in a moment, and found a terrible match. The vertical scale on this graph is from 0 to 5 parts per million. You look at the scale on this graph, it's from 0 to 25 parts per million. The deviations on the average are within about 7 ppm. Many of the shifts are way off. So that's the average. Now, he then went ahead and thought, this guy got the structure wrong. And he had a hypothesis of what. So not only did he think that the synthesis was a fraud, he thought that the structure wasn't even right because it didn't match. So he reinterpreted the published structure of the molecule, the one from the Journal of Natural Products, where they had isolated this molecule and thought it was this structure, reinterpreted the data, and considering biosynthetic factors, came up with what he believed the correct structure to be was. And there, the structure matched, and he did 2 different conformers of it. And there, for this structure, matches within plus or minus 2 ppm average. By 2 ppm average, I mean RMS deviation, root mean squared deviation. So on the average within 2 ppm. So the answer became, not only did James J. Leclerc, what would I say, cheat, forge a synthesis of the molecule, but he forged a synthesis of the wrong molecule, and it was an impossible synthesis. Anyway, it was pretty cool, and the Rachnovsky group was really happy for a while.
Yeah, but who is he exactly? Do we know?
A very unusual character. So the other thing that was interesting, and it's all out there, is if you look at his spectrum of hexacyclinol. Hexacyclinol is a terpene. It has methyl singlets in it, which are big, tall peaks. If you look at his spectrum of his synthetic hexacyclinol, the methyl groups are missing C13 satellites, those little side peaks spaced 125 ppm, 125 hertz, around there at 0.5% of the height, which for a 20 centimeter height peak, you can actually see in a spectrum. So he fabricated this synthesis and his spectrum out of whole cloth.
How do you does he still have I assume this person had his PhD not.
It wasn't part of his PhD. If you go and you earn your PhD here legitimately, and then later on, as an independent scientist working at the Zenobi Research Institute, your own research institute, publish absolute nonsense in the literature, yeah, I don't know.
How did it get published?
Ah, interesting question. A very controversial story.